We're brought to you, as always, by the DiRAC Institute and Astronomy on Tap Seattle. And we're so glad you could join us again for another night of fantastic science. We have a great talk coming up for you. But before we start, just some of the usual reminders. We'll have our Q&A session with the speaker immediately following the talk. So feel free to add questions along either in the Zoom chat or in the YouTube chat if you're following along there. We will also be having our usual Instagram Live interview tonight after the talk at 8 p.m. at AOT Seattle on Instagram. So make sure to get your questions in here in our Q&A or join us afterwards for the interview. So let's get started. Our guest for tonight is a postdoc coming all the way from the University of Western Ontario. Please give a very warm, if silent, welcome to Dr. Dennis Vida. Take us away.
Thank you. So today I'll be talking about the Global Meteor Network, which is a planet-sized scientific instrument. So why do we need to go that big in meteor astronomy? Why does it need to be planet-sized? I hope you can see my screen that I'm sharing. Awesome, thank you. So in contrast to other fields of astronomy, where astronomers apply for grants and they get a lot of money to put into one instrument on one mountaintop, into one telescope, and they get this whole institution working on this one instrument and mining the data for decades after that. Unfortunately, in meteor astronomy, you can't do that. You can put your meteor camera in one spot and you can get 100 meters a night, and then you get clouded out and you have nothing. So that's a big problem, right? What you need is to have as many cameras all over the globe to cover as much area as possible. Because the problem is you can't observe these objects from any point of the globe like you can do for other astronomical objects. So you need to have wide coverage. So today I'll try to make a case for the Global Meteor Network, and I'll tell you why observing meteors is very important. So let's take it off with some background about this field. A couple of hundreds of years ago, people realized that there are two types of meteors that you can see on the night sky. You can either see these huge, big, bright meteors that we call fireballs, and they realized that after that happens, people usually find some weird rocks on the ground that rock looks weird, wasn't here yesterday, so this big fireball happens, so it must be connected. And now we know that they actually come from asteroids. Two asteroids collide, they fragment into many little different pieces, and some of these pieces may end up colliding with Earth, and they just enter our atmosphere and burn up, and they might leave a rock on the ground. On the other hand, people also notice that periodically, or once a year, they can notice a big meteor shower in the sky. So these are meteor showers are caused by millimetre-sized particles. People are surprised when I say that, but that's true. They're very tiny little dust particles, but are traveling at very high velocity. And when they enter the atmosphere, they just ionize the air around the dust particle. And that's basically basically a faint meteor that you can see in the night sky. And these come from tails of comets. Comets are these icy bodies with dust inside them, and they come close to the sun, they heat up, and they start releasing this dust, and that's basically the comet's tail. And if the comet's tail intersects the Earth's orbit, we basically get a meteor shower. One famous meteor shower, for example, are the Perseids, happens every August, around August 12th. Most of you probably, if you know of a meteor shower, it's probably the Perseids. So why do we care about these big rocks? Well, the truth is that if we look on a global scale and look at the big statistics that we've been collecting over the years, it looks like a meter-sized object hits Earth every 2 weeks. By hits Earth, I don't mean it actually reaches the ground, it just enters the atmosphere and just burns up in the atmosphere. But the frequency of impact and the size scale. So basically, if you're talking about something that can cause damage on the ground, well, you probably have to wait several thousands of years for that to happen. But we want to characterize those objects, we want to understand where they are, where they come from, and if they pose any threat. And if we look around, we realized, well, we do live in a very busy neighborhood. There are a lot of asteroids flying around. And from the ground perspective, we have a very unique opportunity to figure out how many of these objects actually enter the atmosphere. And we can kind of provide that one extra piece of the puzzle that astronomers who observe asteroids that are still in space can't do. And we're going to kind of try to calibrate their numbers and our numbers that we actually see on the ground, right? And meteorites, these are the rocks that actually end up on the ground, are very important because they can tell us something about the origin of the solar system. But unfortunately, we don't have a lot of rocks that have been instrumentally observed. What do I mean by that? Well, over the last couple of hundred years, people have found a weird rock. They haven't seen it fall, and they take it to a lab, and a scientist says, oh, this is really interesting. This is a meteorite. But no one really saw it fall, and we don't really know where it came from. We don't have its orbit. And unfortunately, there are only about 50 instrumentally observed meteorite falls, where we can say, oh, we observed this big fireball, we computed its trajectory, and we can kind of shoot it back into space and see where it came from. I mean, virtually shoot it back. We don't really actually shoot the rock itself back. And this tells us about the different, the composition of the asteroid belt. So comparing these 50 observed meteorite falls to the number of total known meteorites, which is in the tens of thousands. So we can see that we're only just beginning to understand where these meteorites come from. And if you want to get a rock from an asteroid, you have two ways of doing it. The first way is you install a meteor network, like the Global Meteor Network, and there are other examples, and they tend to be quite cheap. The Global Meteor Network right now has about 300 cameras, and the total cost of the whole network is about $100,000 because we use cameras that are very cheap. On the other hand, if you want to get a rock from an asteroid, you can send a space probe like Hayabusa 2 or OSIRIS-REx. It's going to cost you a lot. We're talking about hundreds of millions of dollars. And that spacecraft for Hayabusa 2 returned a sample from an asteroid and returned about $5,000. On the other hand, the Global Meteor Network just a couple of weeks ago observed a meteorite fall, which produced a meteorite, which is virtually the same composition and of the same type as the rock that Hayabusa 2 returned. And the difference, of course, is that you can't really choose what kind of rock you get. That's the problem with fireball networks. You just wait until something falls and you go and recover it. But the pro is that you can recover a lot of material, hundreds of grams of these rocks. We're talking about, let's say, tens of ounces or more. And the cool thing is, because you know the orbit of the meteor that you observed, you can actually figure out where it came from in the asteroid belt as well. So you don't really have to send a space probe to do it. But the problem with meteorite falls is that only the hardest parts of the meteorite survive. So you have a rock and you might think, oh, it's pretty rigid. When it enters the atmosphere, everything's going to survive. Well, the truth is that when it's burning in the atmosphere, the air ram pressure is so high that it can literally crush rock. So anything that's not hard enough is just going to get crushed into many little different pieces. It's just going to burn up, and you're not going to get anything underground. And what's also cool is that we can get Martian meteorites, and they're the only samples of Mars we have on Earth right now that we know are from Mars. So the Perseverance rover is collecting some samples. There's going to be another mission in 10 years. They're going to collect it and it's going to bring it back. Or you can find meteorites from Mars. And it's interesting. We know that these meteorites come from Mars because you cut it open and you can actually find trapped gases inside the meteorite. And when people analyze that, they realize, oh, it has the same atmospheric composition as Mars. And it's really cool to have these rocks because we found, scientists found a very old Martian meteorite, which is more than 3 billion years old. So basically, it was ejected from Mars at the beginning of the solar system, and turns out it has 10 times more water than other more recent meteorites that come from Mars, basically providing some partial evidence that Mars had liquid water in the past. And that's basically what the Perseverance rover is trying to answer now, but we can also get that information from meteorites. And also one cool thing that meteorites can provide are some details about how the solar system began. So we know when you take your telescope and you look at the sky and you can see these beautiful nebulae like the Orion's Nebula and the Dumbbell Nebula, et cetera, and these are star-forming regions. And from a meteorite, we actually know, or at least theorize, that a supernova caused this, what we call a proto-solar cloud, a nebula from which a solar system emerged. It caused it to collapse and to kickstart this process of creating the solar system. And it's interesting because this supernova seeded some elements that we usually cannot find in the solar system. So that's why it's very important to find meteorites. Okay, so I was talking about the big stuff, stuff from asteroids, big fireballs, but what about the small stuff, this millimeter-sized dust? I mean, who cares? It's just so small. Well, it turns out when you have a millimeter-sized object traveling at tens of kilometers a second, it has the same kinetic energy as a rifle bullet. So if you're operating a satellite in orbit, you don't really want it to get hit by a rifle bullet, right? And turns out that actually did happen in history. In 1993, there was this big meteor storm of the Perseid meteor shower, and a European Space Agency satellite was hit by a Perseid meteor. It started going out of control. They were able to stabilize it, but they literally had to just abandon the satellite. It just wasn't functional. And also, if you're having astronauts doing some spacewalks, there's a 1 in 5,000 chance of a mission failure per an 8-hour spacewalk. And that is during a period of nominal activity where you can see about 2 to 3 meters per hour. If you go to your backyard and look at the sky, you wait for a long time and you see a couple of meteors, that's nominal activity. But if you have a period of an intense meteor storm, we can see thousands of meters per hour, then of course, instead of 1 in 5,000 chance of getting killed, it's like 20%. It's not like you really want to send people out during this enhanced meteor activity. The problem, though, is that with the current knowledge that we have, we just can't predict meteor showers or the activity of meteor showers that well. And I can just present you one case. In 2011, a lot of scientists predicted an outburst of the Draconiid meteor shower, which is usually very quiet, very low activity, but every once in a while it undergoes this huge outburst in activity. And it was well predicted, well observed. People took out their cameras, characterized, a lot of papers are written, a lot of analysis was done, and it was all nice and peachy, right? And it had a peak of about 300 meters per hour. On the other hand, next year, no predictions were made, but there was this huge meteor outburst that no one actually saw when it was happening. And it had about 9,000 meters per hour. The problem was that it happened over Central Asia, and we didn't really have any meteor cameras there, no observers, so we couldn't really notice what was going on. You would think, oh, NASA must know everything about this. Well, the truth is that it was only seen by a meteor radar that we operate here at the University of Western Ontario, which works 24/7 and doesn't really care about the weather. But the problem is it only sees very, 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 very small, faint and small meteors. Just as a reference, NASA will cancel spacewalks during Perseids and Geminids, whose activity rate is about 150 meters per hour. So this was way, way, way above their limit, and it wasn't predicted. And the problem is that there are no observations. So just to compare how an outburst year looks versus a year of normal activity, you can see these two images. And the problem is, the current state of art is literally people observing meteors visually. You have a guy, goes in his backyard, looks at the sky for an hour, goes to a website of the International Meteor Organization, says, I was in my backyard for 1 hour, I saw 5 meters. And that's how we do long-term monitoring of meteor activity. That is what the Global Meteor Network is trying to change. We're trying to have wide coverage, but to have an instrument that is calibrated, and we can use the data to characterize exactly what the meteor activity was all over the world, 24/7 for a long period of time. So we can make better predictions of meteor showers in the future, because if we want to be a space-faring civilization, we have to understand what the near-Earth meteoroid environment is like. And that's why, as I said, we need a globally distributed scientific instrument. We cannot have just one camera in one spot and just pour hundreds of thousands of dollars into this one camera. We just have to have a lot of cheap cameras that are all over the world. And what we found is that the most difficult part is logistics, basically deploying and maintaining these systems. Right now, my research group has a technician. When something goes with one of our professional grade cameras, he has to sometimes drive for hours to go fix it, and then maybe come back and then go out again to deploy it. What we're trying to do is we're trying to put these scientific instruments into hands of amateur astronomers, so they can deploy them, and if something goes wrong, they can easily maintain them. We designed it in such a way that parts are easily available, and the whole system can be fixed pretty easily. So this is how the system looks like. It's nothing spectacular. The whole camera is about $450, and it's basically a fully automated system for meteor detection, calibration, and data reduction. So basically, you have this raw video in, and the method goes in, detects meteors, and then calibrates it against the background. It knows exactly where it was in the sky. It measures the brightness exactly, and then reports it to a server where we compute orbits and do all sorts of analysis. The whole project started in 2018, and right now we have more than 300 cameras in 22 countries. As for the hardware, if someone's interested in that, we're using Raspberry Pis. So it's a $35 computer, and we're using very cheap but extremely sensitive security cameras with various lenses of various fields of view. And in our kind of standard setup, we have a camera that can see 25 frames per second and has a stellar limiting magnitude of +6, so which is kind of comparable to human vision. So it only took decades of work to achieve what's comparable to a human, but we're finally here, and the whole system in parts is about $250. And we also have we also collaborate with a private company that sells plug-and-play systems. Now, as for the software and data, we found that a big problem in our field was that methods were not transparent. So we wrote all software from scratch, and it's open source. You can find it on GitHub, both software that runs on the cameras and the software that computes the trajectories and does the analysis. And also all the data that amateur astronomers from all over the world collect is completely open. Within 24 hours, more or less, everything gets published on our server. So if there's something going on, some big meteor shower outbursts or whatever, the community can know and characterize and understand the event that's happening. And this is a sample of the data we're collecting. Upper left shows an average kind of stacked frame of 256 frames in a very, very nice location, Canary Islands, La Palma. On the right, you have an example of a meteorite dropping fireball that we had here in Ontario about 2 years ago, I think. And what's very interesting, we can see all the little details of the fireball, and you can actually see those two little fragments at the end, which is very important to know where the fragments are, how big they are, and where you should go to find them. We also observe a lot of meteor showers, thousands of meteors in one night, which again helps to characterize their activity, which is what we're trying to do. We also see a lot of TLEs like sprites and nelves. We don't really do much with this atmospheric phenomena, but the data is saved. So if anyone in the audience is interested in doing more about this, we're more than welcome to share the data. And we also make sure that our amateur astronomers, our collaborators who host these cameras have something to see. So the systems every day create a couple of very interesting reports like this one, which basically show them the activity of the meteor showers. And we're trying to provide some attractive graphics that they can share in social media and feel more involved in the project, instead of, us saying like, oh, here's the camera, put it in your house, just send the data and that's it. We want to make them feel involved in the whole project to make them understand how important the work that they're doing is. As for processing pipeline, in an average 12-hour night, the whole network processes about 250 to 300 terabytes of data, and everything is done on these little Raspberry Pis. And only a couple of tens or hundreds of megabytes per station are sent to the server, which computes the trajectories and produce the results. This is the current sky coverage of the Global Meteor Network. As you can see, we have a lot of stations in Europe, especially Central Europe. We have a lot of stations in New Mexico, Arizona. We have the Lowell Observatory there, who's deploying a lot of cameras there. Of course, we have some stations here in southwestern Ontario, but because the weather here is so bad all the time, it's like we're not. New Mexico is awesome. And we're, of course, trying to install more cameras, especially in the Southern Hemisphere and in Asia, to get large longitudinal coverage. And since the beginning of the project, we've recorded more than 150,000 meteor orbits. And here on this heat map, you can just, these individual dots are different meteor showers that we're trying to characterize. And in final notes, of course, the most valuable thing from my perspective as a scientist is what kind of science we can get out of this data and out of this project. And of course, that's also been very productive. We also try to answer the question of gravitational focusing. So what that basically means is that you have a meteor shower and Earth's gravity focuses the meteors into one point. So if you have a satellite passing through there, it can get just absolutely pummeled by meteoroids that are flying through space. So the network actually characterized the dispersion of meteor showers and showed that's actually not a big problem, as people have thought before. The enhancement, the increased number of meteoroids in that little kind of thin line behind Earth is not hundreds of or thousands of times more than nominal, but it's actually about 10 times more, which is very, very significantly less than before. And that is my talk, and I'm willing to take any questions. Thank you for your attention.
Thank you so much, Dennis. I'm going to clap for everyone that I'm sure is clapping as well. What a great talk. We did have one comment in the chat that Barker says that they're in Nelson, New Zealand, and would be keen to take part or host a camera.
That's great. Yeah, just Google Global Meteor Network and you will find us, and you will get in touch with me, and we'll take it from there.
Sounds like you've, adding to the fan base now of the Global Meteor Network.
That's right.
So we don't have any questions yet on Zoom, but feel free to add them, everyone who's following along. So I'll take my purview as the host to ask. I don't think you mentioned this, but I was really curious. Like you talked about, the two methods of, either collecting asteroids that fall to space or those, that you send Habayasi or other probes to collect. And is there any issue when those asteroids do fall, about like ownership of the asteroid in terms of where it falls, like if it falls through somebody's roof, which I know is super rare, but I'm just wondering if there's some kind of what can kind of happen when you're tracking an asteroid and it falls somewhere that isn't readily accessible in terms of like private property.
Yeah, well, meteorite laws are very interesting, and every country has a different meteorite laws. Most countries, I think US and Canada, it's basically if it falls on private property, it's basically that person's property. But if it falls in public land, then you can claim it. Some states, I think, you can actually buy mineral rights, and if you find any meteorites, they're yours. On the other hand, some countries, they don't really have any laws. For example, Spain, we had a meteorite fall there recently, which was kind of contentious, like who gets to keep the rock. And countries of the say ex-Soviet bloc, they have a very interesting law where it says when the meteorite reaches velocity 0, it becomes the property of the state. So goes through a roof, destroys everything, not the state's problem. But once it stops, they take it.
Wow. Okay, that's so interesting that there are like, I mean, it makes sense that everyone's kind of deal with this in a different way, but that's really curious. Thank you. So we
and the countries where where if it falls in private property, the owner keeps it. Well, in those countries, a lot of meteorites are found on roads next to someone's property. People just take it and put it on the road. It's like, oh, yeah, I found it on the road.
Ah, I see. So there are ways to work around and get those asteroids for science. Cool. Well, we do have one question from Barker who wants to take part of this network. How many recovered meteorites have come from network observation?
Oh, yeah, that's very interesting. Well, I would say about tens. There are some cases where networks didn't observe a certain meteorite. So we have 50 total, right? And there's some, and I'm actually working on a couple now where you don't really have any what we call instrumental observations, but a security camera caught it or a dash cam caught it. So then we have to work really hard to calibrate those observations and compute the trajectory and the orbit. But meteor networks are kind of the primary source of those, say, instrumentally observed meteorite falls. And we're trying to increase those numbers because it's infinitely more easier to calibrate a video from a kind of a scientific grade camera than it is from a casual recording.
So Dennis, I was going to ask a couple questions as well.
Yeah, go ahead.
So first off, I don't know anything about atmospheric phenomena other than the clouds because we live in Seattle and we have lots of them like you do in Ontario as well. So what could you just say a word about what sprites and elves are that you're not using, but they just looked so amazing?
Yeah, they're really cool. Well, I'm not an atmospheric scientist. So anything I say, it's, just don't take it as something, set in stone or something, right? You should really read up on this for yourself. But as far as I understand it, there are lightning that it's a type of lightning doesn't go from the cloud down, but it goes from the cloud up into space. Apparently, it discharges into the Van Allen belts. Maybe, I don't know. Probably atmospheric scientists know more. But what's really cool about them is they seem to be correlated with lightning. So, for example, like lightning happens and then they occur a couple of milliseconds later and just go up. And they seem to be concentrated in certain areas. For example, most of the observations that we have are over the Mediterranean, over close to Italy, but some other places don't seem to have them. And what's interesting about the sprites is that they last a fraction of a second, just a couple of milliseconds, and they're red, and they look like squid, or not squid, but jellyfish.
Wow. Okay, that's totally fascinating.
Yep.
And then a question that I had was, do you get false? I mean, so this is obviously sort of a false positive for your system, for your software. Are there other interesting ones? I mean, I can think of like airplanes, or fireworks are popular here in the U.S., or like even glints from bright satellites. Like there's been a lot of press about Starlink. I don't know. Have you guys caught any Starlink trains?
Yeah, actually, when Starlink was just starting, it looked like the apocalypse. And we thought, oh, geez, we're just gonna have this, the whole sky is gonna be filled with these things. What are we supposed to do? But fortunately, they changed things, and now everything's fine. We don't really notice them. But usually, satellites are very easy to filter out. For this, it's very simple. You just look at the angular velocity, and they're all below 2 degrees a second, but everything above 2 degrees a second, that's mostly a meteor. So we just have this kind of hard threshold, and that gets rid of satellites, no problem.
Interesting. Airplanes too, I suppose.
Well, airplanes are different. Our systems have like a dedicated fireball detector. We just realized that these faint meteors are much different from big fireballs. So we have two different software pipelines that detect each. And the problem with the fireball detector is that it's looking for something that's very bright and slow, because these meteoroid dropping fireballs tend to be slow. And that's how airplanes look like, especially those they're like approaching the runway.
Right.
It's really hard to filter them out. But we have students that are working on machine learning methods to filter them out, and it's actually incredible. I think once the paper is published, it's going to be kind of the landmark paper of how machine learning should be done, because the accuracy is like 99.98%.
Wow. Yeah. We got a question from the YouTube chat here. How dark do your skies need to be to participate in this network? Do you need to be away from the cities, or just to personalize it, could we do it in Seattle? I noticed no Seattle in your map.
Yeah, well, that's actually not because of bad skies. Believe it or not, it doesn't really matter. You just choose a different lens. So if you have very dark skies, you can use this wide field lens. We have stations all over the world in very dark conditions. So you get about 90 times 45 degree field of view, and you go down to magnitude 6, no problem, at 25 frames per second. But if you have very light polluted skies, what you simply do is you just take a narrow field lens. And that just takes care of the problem. So we have a couple of cameras in Brussels, in Belgium, which apparently are the world's worst light polluted skies. It's just absolutely terrible. And these cameras are just working fine. They're just observing a much smaller part of the sky.
Oh, wow. So that sounds like Seattle's on the menu then. That's great.
Yeah, that's right. It would be great if we could get some cameras there.
And another question from YouTube: why don't more governments pitch into these sort of global meteor network resources?
Yeah, that's a good question. Well, it really depends on what the legislation is interested in, but there are a lot of projects all over the world which they do get government funding. One of probably the biggest one is in Australia right now. They call it the Desert Fireball Network, and they're just doing amazing work. And it's really interesting. Their main goal is to recover meteorites. And when you're in Australia, in this Australian desert where the sand is orange or yellow, and you're looking for a black rock, that's really easy to do, right? But on the other hand, if you're looking for a tiny black rock in some sort of European forest, or in Ontario, that is really hard. So what they actually did in Australia is they populated the desert with lots of these fireball systems, and they get one fireball every couple of months, and they just go out there, and it's so easy to find. They actually drive on an ATV and just like, oh, yep, that's right there. They actually found one when they were they were flying a light airplane. They just saw it. I was like, yeah, that's a black rock there. Just no problem to spot it.
That's so great. I can definitely see why that would be easier than finding them in a forest. We have another question from the Zoom from Ken Birkin. Can you please talk about the contamination of recovered meteorites? Are they still pure on the inside? And can you kind of tell what the contamination is and isn't?
Yeah, that's a really great question. So the reason why we install these fireball networks is so we can recover meteorites fast. So say before any rain, before any damage to the rock, so you can go there and it's like it's almost as if you kind of picked it out of space. Almost close. It's not entirely the same, but close. So contaminants, probably the biggest problem is water. For example, a lot of meteorites have a lot of iron. So water gets in, starts cracking, especially if it freezes and it just the whole meteor just can break apart. We had a case in the year 2000 when there was this big fireball over British Columbia or Yukon territory, and meteorites fell on a frozen lake. And the guy who was living by the lake noticed this and goes and picks up a couple of rocks and puts them in a plastic bag. And turns out these are kind of the most pristine meteorites that we have right now of this particular type, which is very special, et cetera, et cetera. But the problem is that there was also much more material there that he just didn't see, didn't have time. So when people came there a couple of months later, what happened was that these rocks, because they were dark, they heated up in the sun, they melted through the ice, and it froze over. So a couple of months later, people from my research group were there with chainsaws trying to get the meteorites out, and they just destroyed it. They had this kind of thing to take this kind of sludge that the rocks created to try to salvage something. So it's just hilarious. But yeah, things can happen, and that's why we want to act fast, have good instruments, good understanding, a lot of expertise, and then just accurately predict the location of the fall, send people there, find it, put it in the lab, and that's it.
We've got another one from the YouTube side. It sounds like, Dennis, you're doing a really good job selling this this network. So some more questions about specifics. So you've said you don't need necessarily dark skies, but one person asks, could we mount a camera on our camper van when we're out stargazing? Does the location of the camera need to be fixed, I guess is the question.
Yeah, well, actually, yes. The location needs to be fixed because I make an initial calibration of the camera for a particular location, and then it recalibrates itself, but the location needs to be fixed. So it's not ideal if it moves.
So a camera driving around is not so good. Okay.
Not a good idea.
We got a couple questions from Mark on the Zoom. So the first one, does there appear to be any correlation from observed fireballs with radar observations?
Mm-hmm. Yeah, well, we actually can observe fireballs with the radar. And that's the problem with fireballs and radar observations is that it doesn't happen often. Fireballs are so rare. And to get like a good radar echo, the geometry needs to be perfect. So the way the radar works is you have, at least our radar that we're operating here, you have a transmitter and a couple of antennas, and you only get meteors that have a specular reflection, which basically just kind of special geometry. So the radar sees very faint meteors, but the problem is it only sees a small portion of them because they need to have the right geometry. So radar is not an ideal way to observe fireballs. We like to observe them with cameras because they're much more precise. Also, the radar is not very, very accurate in terms of the orbit.
Okay, this kind of tacks on to that. And the second question, could methods such as like air traffic or weather Doppler be used to locate potential falls?
Yeah, so the weather Doppler actually can be used. That's very interesting. So you have, when a meteorite fall happens, most fireballs, they end around a height of 20 kilometers, more or less. And meteorites fall down and they turn off. You can't see them anymore. That part is called a dark flight. So they're luminous down to about 20 to 30 kilometers. If the meteorite is really big, down to let's say 15. But after that, they produce no light. but they can be picked up by the Doppler radar sweep. And especially if we're talking about like smaller meteorites, smaller dust particles, you can actually see, and meteorites were recovered that way. It's a really cool method, but you need to have a Doppler radar nearby the fall. If you're looking at something that's very far away, then the Doppler signal needs to travel through a lot of atmosphere, and then it can get distorted because of clouds and other weather phenomenon. So the method definitely has its applications, but it's not universal.
One more short question on the YouTube side. Did the cameras have support for filters for streetlight pollution, or is that also not an issue, just like the air pollution?
Yeah, it's actually not a problem. We don't really need any filters for that. We actually want to remove all filters and have just an exposed naked sensor. Some people forget to take off their IR filters, and it's funny, but meteors emit a lot of light in the infrared. So it just needs to be as clear as possible. Light pollution is not really a problem here, because contrary to how astrophotography is done, where you have long exposures and you're integrating a lot of light on your sensor over a long period of time, and that's where light pollution kills you. These cameras operate at frame rates of like 25 frames per second. So it's not really a problem. Light pollution just can't integrate that long. And the star and the meteor signal is quite strong when compared to the background sky.
And people on YouTube are getting more creative here. So now, which I love. One user says they've got access to good dark skies, but solar panels and batteries. Is there any power requirements? You said it worked on a Raspberry Pi, so I assume that low voltage is not a problem.
Yeah, I mean, if you can run a Raspberry Pi, then it's no problem, because these cameras are very, very low current. We're talking about like 500 milliamps at like 12 volts. That's very, very low. So I think you should run should be able to run the solar panels, no problem. And we have a couple of people in the network that deploy systems like that. We completely kind of opened the design and parts and everything we use, so people can just do whatever they want. There's some really cool things that people do. One guy just integrated the whole thing into like the wall of his shed. It has like a big screen and some buttons and stuff. People love to do stuff like that. It's awesome.
And to be clear, the people, for most people in your network, people pay for these. These are things that people are volunteering to build themselves, right? To participate. This is not something you're sending out to them.
Yeah, exactly, right. I mean, if you want to build everything from scratch, I think it's like $200, including the Pi and everything else. And that's, I think, well within every amateur astronomer's budget.
Okay, I think that was it for our YouTube questions and our Zoom questions. So I just have one last one to kind of end the, oh wait, actually, no, I'm sorry. We had one more question from Ken. How many meteors are you being notified of on an average day, or like a 24-hour period around the world? Does it vary a lot? And do you get more data during these various, annual meteor showers like the Perseids and the Geminids that you mentioned? And kind of additionally, do these cameras report continuously, or do they like batch things and report them kind of more periodically?
Mm-hmm. Yeah, so they start observing after sundown. They observe all night, and in the morning they finish up processing and then upload one archive to the server, one file to the server, which can range from like 10 megabytes to sometimes a gigabyte, depending on the meteor activity. Usually we see about, let's say, 30 to 50 meteors per night, a normal night if it's clear. But during a big meteor shower, we had like 1,400 meteors per one camera, really just a huge number. So, when you combine that into, you combine the whole network, I think for the last year's Geminids in December, we had a total of like 6,000 orbits in a day or something like that. It's really, really impressive. It allows us to do a lot of science that otherwise we were not able to do just because of the sheer numbers we have.
Wow, well, thank you. I think we are just perfectly out of time, so I'll have to save my question for our Instagram live interview, which will be happening at 8 o'clock. For those of you joining us on Zoom and YouTube, you're welcome to join us there at 8 p.m. We'll be doing a less formal Q&A session with our speaker, Dennis Vita. Thank you again for a fantastic talk and for answering all our questions. And for everyone else, we thank you for joining us, and we'll see you next month.
Thank you for having me.